signal processing or digital signal processing, DSP. So this is the outline. I mean, start with introductions, then the digital signal processing in time domain, frequency domains. What does it mean? Then we have also, if you want to go through this time to frequency, you have to go through these windowing functions. So we want to look into what is this and how it will affect our accuracies of the data, okay, digital signals, data that undergoing these processings. Then we have also frequency and time domains analysis available. So different types of analysis to look at. Finally is on averagings and overlappings. What are these? So the signal itself, you don't just take this one set of data. It could have a few sets of data, then you do some average to get a more consistent or repeatable results. Then finally is one of the DSP techniques where it used to diagnose the problems of the machines, particularly on those very effectively to detect faults that probably it gives a repetitive types of impulse when there is a fault develops in that machines components during rotating during running or in service. Then that fault itself basically every revolution or every rotation itself, it will create a kind of impulse or impacts, knockings, impacts that repeatables, repetitive of this impulse every rotations. So can be detected through some digital signal processing techniques and on that vibration signal itself. So it can be pinpointed to a certain machinery faults. Okay, so you will see these digital signal processing techniques later on. Right, so we look at the classification of signal first. Okay, we have analog and digital signals. Two types of analog and digitals. So analogs, of course, you know that it's continuous signal in times. So it's like what you have seen here, So continuous signals in times, and you could have this analog display on analog signal representations. So this analog signal could be a discrete signal in time also, but it is based on samplings. So if you continuous signal, you do a sampling, then that is still an analog so-called signal, which is in discrete. So you could have in discrete time waveforms. So analog signals in general is a continuous signal. So digital signal, basically, if you've already gone through these discretizations of your signals. So of course, here is referring to a discrete time signals. So here, your digital signals is represented by samples. So you have samples, all these samples are your digital signals. So digital signal is discretized in terms of times. If you put this signal over time, so you discretize in terms of times, sorry. So that delta t, or the time between the two samples, is delta t, decided by your, if you still remember, decided by your sampling frequency or sampling rates. So 5,000 sample per second. So you basically every 1 second you have 5,000. So in between two sample is 1 over 5,000, which is your delta t's. So that is discretizations in terms of what we call times. So you also discretize the magnitudes of your physical variable. So amplitude itself. So it's quantizations of your amplitude or magnitude of your vibrations. Here is any variables. So that is also yeah, under digital signal. Basically, we do discretization in its time domains, time axis as well as the amplitude axis. Right. So coming back to these instrumentations of vibrations analysis. So this part we have covered. So all analogs coming out here will be digitals. So now going here, that is what today we are looking into, and we are now at number 4 in your processor, in your PC computers or analyzers that where through everything is digital signal where we can process it using digital signal processing techniques. Okay. So whatever coming here, if you still remember, is time domain signals. So from your vibration itself, let's say we look into a simple harmonic signals. So you have a continuous signals, then you have a DAQ coming up is a digital signals. So it is still giving the same signals. It should give the same signal as actual analogs that you measured by your sensors. So your digital signals should also show the same, but basically is in samples. Okay, it should give you the same amplitude, discretize into the same amplitude and same times at same time. Okay, so that time itself is t itself should give you the same. Then this t itself, the inverse will get you the frequencies. All right. So time domains, if we are looking into a simple harmonic motions, like I mentioned, like I have sketched it just now, one cycle is your times, right? Then 1 over t is your frequencies, okay, in hertz, or we multiply with 60, then it's in RPM. Okay, so if you can measure a simple harmonic motions, then it can be easily be measured, okay, the frequency, the amplitudes, as well as the periods, right, the cycle. So if you have a system, I mean it vibrates, it's vibrating, or its motion is basically convoluted, or what we call superimposed by two different frequencies. So the time waveforms that you will see, or the vibration signals, you will see is some sort of like this, giving you a high frequency components, low frequency components, and high frequency components superimposed together. Right. So if you are getting original form of vibration signals, it could be convoluted by many frequency components. So it's difficult to analyze. Okay, you have many frequencies superimpose each other together. Okay, so difficult to analyze, and your real worlds or real actuals, so-called time domains waveforms is very complicated, it's very complex, and uh, but it can be separated into a simple sine waveforms. Okay, like I mentioned to you. Okay, here, so here you can have one sine wave. You can split into one a low frequency sine wave in this case, right? And a high frequency sine wave. Okay. So it can be split. Okay. So when you can display, you can split it, then it can be displayed in terms of amplitude over time or amplitude over frequency. Then it could be easy to analyze in this complex vibration signal what type of frequency component you have in these particular complex vibration signals. All right. So looking into a time domain and frequency domains. So whatever coming in from your DAQs, from your sensor itself, and you are measuring dynamic signals, okay, if you are measuring a very simple harmonics motions, so it will just give you a one sine wave, as you can see here. So from here itself, one cycle, 1 second, immediately you know this is 1 Hertz. Or if you can transform it to frequency domain, then you know that at one amplitude over frequencies, so you know that at 1 Hertz, you have one peak at one amplitudes, right? So if you could have two cycle in 1 second, then it's 2 Hertz. So you have another peaks. So this is a 10 cycle in 1 second, you have 10 Hertz. So you have a peak at tens, right, in frequency domain. So that is how you see, okay, from time domain to frequency domain, how it can be represented. But in actuals, it could be a combination of these three, okay, superimposed together, where in time domains, okay, probably you did not see, okay, what type of how many frequency, okay, convolutes or superimposed together in this signal. But if you are doing a frequency domain, or you look into a frequency domain, you know that, yeah, inside this signal itself, you have three frequency components. One is 1 Hertz, the second one is 2 Hertz, the third one is 10 Hertz. Okay, so that is how you look the problems, the vibration signals in terms of times and frequency domains. And why we need frequency domains? So we are saying that it's complex in nature. I mean, in actuals, it's complex. So it won't be like, in actual, you won't just see a pure sinusoidal function where you can easily analyze the frequency amplitudes. So it's something like this, or to be more complex, it could be something like this, right? So you cannot really see what types of how many frequency components basically superimposed in these uh, signals itself. Okay, so the best way to do is you can look into a frequency domains, as you can see here. So you can separate each frequency component into in terms of frequencies. So, and you know from here what is this frequency available at here, frequency frequency component available at here, these signals, and what is the amplitudes. Okay, here you know that 10 Hertz is the highest amplitude, something like this. So similarly, complex time domain signal can be visualized in frequency domain using. So how you use it? So we are doing this Fourier fast Fourier transforms. Okay, fast FFT transform. Anything from time domain through these frequency domains algorithms. Fast Fourier transforms, which is a discrete algorithms. So in the discrete digital signal going through this fast Fourier transform, it will give you your signals decomposed into a frequency domain, which is amplitude over frequency chart. We call it spectrums, right? This is amplitude over times. FFT stands for fast Fourier transforms, okay, algorithms that compute the time domain signal and convert it into the frequency domains. So the time domain solution can be transformed into frequency domain using Fourier transforms. Okay, analog signals. Okay, you can convert any of your time signals, analog or digital, using Fourier transform algorithms. If in the case of analogs, Fourier transform can be used. Okay, if it's a discrete signal like a digital signal like what you have, then you have to use a discrete Fourier transform or fast Fourier transforms. So if you are in the frequency domains, as you can see here, then how basically it tells us, okay, the information here, frequency domain, we call it spectrums, vibrations spectrums itself. It is y-axis is your amplitudes, x-axis is your frequencies. So whatever complex, how complex is the time domain signal when it transforms to frequency, then it will be represented by that frequency components. How wherever appear in the time domain, it will basically show, okay, as a peak, okay, in the frequency domains. Then The y-axis is the amplitude, or what we call the severities. So basically, it can be represented same like your time domains. It can be displacement, velocity, or accelerations. The highest, the peaks in the frequency domain, basically it tells us is higher vibrations in that particular frequencies. So higher vibration means higher severities. Okay, so whatever peak that you see here is the frequency component set available, okay, in the, the digital signals that before you convert or transform to a frequency domain. If you are converting to a linear quantity, your quantity is the linear quantities. So then the dB in terms of your linear scales, V voltage. Basically, why you convert to dB basically is with it is relative, or is compared with a reference signals. So here you know that if it's positive, then you know that is larger, your so-called your log positive numbers is your logs with reference. I mean, if your V is larger than your reference, so then it's a positive dBs. So if it's log 1, it is 0. Log 2, you have a positive value. If it's a log below 1, then log 0.1, then you have a negative value. So the whole idea is when you convert to dBs, okay, then come with the reference. Okay, this reference basically you can compare, okay, to tell you relatively, okay, these particular components at this particular peak itself, okay, how it compared to, let's say, your noise floor, okay, your noises levels, okay. So if it's dominance, then you have a positive dB. If it's below the reference values, then it's a negative dB. So that is another way of representing our spectrums in different scales. Okay, so it's your quantity is a linear, then basically you use 20 log V over V reference. So if it's a power quantities, if you are in a power spectral densities, then auto power spectrum, then you already square. So then you do not really need to multiply with the 2, okay, because it's already the quantity itself is a power of 2 already. So here you only need 10 logs V over V reference. So for example, this case, if you want to calculate the value of the motor speeds, sidebands of 1 mm/second to center frequency 20s, right? So here is a linear quantities, 1 meter per second to center frequency. Your reference is 20s, so 20 logs 1 over 20. So you know that's your sidebands contributions towards the central frequencies. So if you have usually, so this motor itself, you have frequencies. Okay, let's say at here is 10 mm per second. Then it due to some faults, it will give you additional so-called frequency components at at the site of this center frequency, motor central frequency. So this frequency itself is probably you have a gaps of these frequencies a fixed probably this is 50 hertz. Let's say maybe this is a 5 hertz difference. Okay, every 5 hertz you see this sideband, a peak beside the central frequency, and here is referring to the value is in linear is 1 mm per second. So from here you know that how, okay, if you take this particular peak as your reference itself, you know that these side bands is these frequency components is negative. If you plot in dB itself, dB, this is linear, this is dB, right? So you can see that at these particular components itself, you will see a peak if you use 10 mm per second as a reference. So you will see a peak at here lah. Okay, you will see peak at here. Okay, coming down. So probably something like what you have seen here. Okay, here, here, here. Okay, so all below at that particular peak itself, this particular peak itself is 0 because 10 over 10, log 10 over 10 is 1 is 0. So whatever below these zeros are negative values of dBs, meaning these particular frequency components or this particular sideband itself is not dominance, okay, or not higher than this particular frequency. But in the case of you have a frequency at here, which is at here itself, so you know that's at in dB, so you know that there is one peak, okay, going positive dB. So you know that in this case, it is higher dominance in these frequency components compared to your so-called reference amplitude frequency, reference amplitudes, right? So using 20, here is using 20 log 10 V over V reference, then you know what is its amplitude in dB. So that is another representation of the spectrums. Conventionally, it can be easily represented in linears, okay, but then sometimes you will see this in dBs, especially when you want, okay, to compare it, okay, with the certain amplitude reference, right? So Fourier transforms, okay, if you want to transform your time to frequencies, then Fourier transforms is used, okay. If it's analog, you use Fourier transforms, and any time domain signal, no matter how complex, as long as it's repetitive, it can be represented as a linear combination of simple harmonic motions of varying amplitude, varying frequency, and varying phase. So no matter how complex, you can still transform it to frequency. So whatever in frequency is represented by a combination of simple harmonic motions. Okay, so all frequencies, simple harmonic frequencies will be displaced in terms of frequencies axis. Okay, at a different frequency, different amplitude, or even different phase. All right, so conventionally, okay, if mathematically, if your signal is this is the Fourier transform algorithms, equations. So in under your analog signals, okay, is continuous, right? So if it's continuous signals, then you can use these equations from negative infinity to infinities to transforms, okay, your time domain signal xt to your frequency domains x, f, okay, your spectrum. Or you can do the inverse Fourier transforms from the frequency to the time domains. Okay, so to do this, okay, it requires your signals is a continuous or infinite times, okay. But if you remember, here we are in digital signals. Is a discrete or digital signals. You have a finite length of signals. Okay, it's a finite times. Okay, you have a length. okay, a finite length of this particular for this particular signal itself. So here the Fourier transforms not suitable, so we are using this so-called discrete Fourier transform. As you can see here, is represented by a number of samples. So it takes depends on how many samples that you want to take to transforms, okay, to convert it to a frequency. So you can see that this n itself is basically the signals, okay, in digitals, okay, discrete Fourier transform is all for digital signals or discrete signal where you have all the samples. So here, if you want to convert to a digital signal to in time to frequencies, then we need to decide, okay, how many samples we want to take and convert it to digital signals. So it's you have a finite length of signals. So discrete Fourier transform and fast Fourier transform are same. So fast Fourier transform basically is with the highest capabilities of computing powers. So now is called fast Fourier transform. So here, if you are doing fast Fourier transforms, it is a discrete Fourier transform, a type of discrete Fourier transform. So if you are taking care the discrete signals in this case. So if discrete signals, then it have to be a finite length or finite times computations, okay, of a Fourier transform calculations. So discrete finite, it have to be finite length. Then FFT, you don't go for a full continuous signal or infinite length. It have to be a length of signals, okay, that we want to analyze or convert to a frequency domain. So that is why the algorithm you have seen here, the n's number of samples that we want to convert. So this FFT method is also called butterflies because it only gives half of the results. So positive and negative frequencies. So you can see that is a mirrors, okay, of one sets of one parts of the frequency components. So you have this negative frequency or positive frequency component. So here you only use the positive frequency results components, right, in this case. So if you as I mentioned just now, okay, if you want to convert your digital signal in time domain to a frequency domains, then under these fast Fourier transforms or discrete Fourier transform, then we had to decide the number of samples to be used to convert to these frequency domains, right? So in many commercial analyzers, commercial measurement systems, so they don't represent this so-called number of samples that you want to use for frequency domains, okay, for converting to frequency domain from time domain. In fact, they are using these numbers of lines, okay, or FFT lines in this when it converts to a frequency domain. So what I want to say here is sums, okay, if you are, because I mentioned to you, okay, you want to convert, you need to know, okay, number of samples or number of point you want to use, okay, if you have a signal, digital signals, okay, digital signal in time domains, you want to go into a frequency domains, okay, through FFT, right? So you first going through this FFT, you need to decide how many samples I want to convert it. So for example, here I want to take this size, okay, 1, 2, 3, 4, 5, 6, 7, 8, 8 samples, okay, to be converted to take it as one blocks of signal and I want to convert it to frequency domains. So if you know the number of samples, then you basically you can decide, okay, how many samples you want to convert to frequency. But in many commercial analyzers, they don't tell you a number of samples. Okay, they only show in terms of FFT lines. Okay, so they are equivalents, same number of samples or the FFT lines are referring to the same things. Just that number of samples is basically the samples in one blocks, okay, in this particular block itself that you want to convert to frequency domain. The FFT line is basically is just a box number of samples divide by 2.56. Again, you still remember we say that it's a butterfly, it's cut into the half, okay? So the FFT line is referring to this particular half, or to be exact, is less than this particular half. So here is referring to the useful FFT line is referring to these useful frequency components that can be used to analyze. Okay, so it is greatly related to your number of samples that you use to convert to frequency domains divided by 2.56. So that gives us our FFT lines. So if you can see the tables, 256 divided by 2.56 is 100. So you have 100 FFT lines. The half of it is one. This is, let's say this half of it is got how many samples in this particular is 256 samples. So 256, half of it is just 128. So you know that 128 is gone. Okay, but to be exact, only the useful one will be only referring to hundreds in this case. Another 28 here is also not usable. Okay, so that is what it means. Right, so it's also related to the aliasing effects. You still remember the aliasing effects, it cut off. You have this anti-aliasing filter that it cut off half of the frequency that you can use, right? So in frequency domain, that half of frequency you won't be shown, but it will replace by the mirror image of this particular so-called signal in frequencies. Then that particular half won't be any useful. It's just a mirror image of it. And because of the upscale oversampling factors in the analog filters of anti-aliasing filters, so it also don't give you exactly the half. It's only 2.56 divided by 2.56. So similar things. So this FFT lines itself, it can help us basically in that particular frequency range. Okay, these FFT lines basically telling us uh, uh, let's say okay, we have sampling frequencies. Our sampling frequency is 1024 samples per second. Okay, when we capture in time domains, so we have 1024 sample in 1 second. All right, so this one we have discussed earlier. Right, then due to these Nyquist theorems, the useful, what we call the useful frequency components, or F max, is 1024 divided by 2.56. So it's 1024 divided by 2.56, only 400 hertz. So useful, if you want to convert this through FFT, you want to convert into amplitudes. This is over times, amplitude over time, amplitude over frequencies, right? So because of these anti-aliasing filters, okay, you won't get 1024 hertz, right? Half of it only, less than half of it, and because of this oversampling due to these analog filters, low pass filters, you get less than half of it. So it's 2.56, 400 hertz. So here it means, let's say this is 1024, so you only have half is 512, right? But you only have the useful is up to 400. Okay, so I add here in frequency domains, what you have seen earlier in frequency domains is also a digital signals. This is also a samples. This is built by samples. Okay, if you are in digital domains, so here are all in samples. All right. So remember, you want to convert to frequency domains, you have to FFT. You have to go through this FFT. Then you have to decide how many samples I want to use to convert to frequency domains. So in this case, if I'm using uh, every 1024 samples, okay, I want 1024 samples converts. 1024 samples converts to I collect 1024 samples, then I convert to I convert to frequency domain through FFTs, right? So meaning here I have from 0 to 1024 hertz in frequency domain. I have once I could plot one samples, okay, right? 1024 samples, but in frequency domain, right? So I can have 1024 uh, up to 1024 frequencies. I have 1024 samples up to 1024 hertz. So in this case, I only have 400 samples. I mean, useful sample that can be plot in 400, 0 to 400 hertz. So in his case, I have only 400 samples that can build me the spectrums, the peaks. All right. So that is what it means. So if you are asking your F max is 400, and you are using 1024, your FFT lines, this is your number of samples that you use to process FFT. So FFT lines here is against 1024 divided by 2.56. So it's equals to 400. So meaning under your useful 0 to F max, you have 4 in frequency domain under your useful frequencies F max 0 to 400, you have 400 line, or here is referring to the samples that can build your frequency spectrum or domains. All right. So in this case, the resolutions in your frequency domains. So let's say this is up to 400 hertz only. Zoom in, zoom in. Okay. So this amplitude. Then just now we say that from 0 to 400 is my F max. Okay. So 0 to 400 hertz, I have 400 samples that can build my frequency domains spectrums. Right, so I have 400 samples or lines that can build this frequency domain. So this in between sample to sample is our delta F is equals to 1 hertz. Okay, so that is what we call the frequency resolutions. Frequency resolution referring to the number of lines used in the frequency spectrums. Here is how many samples that you have in your 0 to F max. Okay, that is your FFT lines. Okay, so another words, frequency resolution is also called this bandwidth, BW, bandwidth, smallest increment in your frequency FFT spectrums. So how you get it is your uh, Fmax, okay, divide by your FFT lines. So if I want to know my BW, okay, or my delta F, then I can get my Fmax divide by my FFT lines. So in this case, is 400 divided by 400 is equals to 1 hertz. So that's why every 1 hertz you have 1 samples or 1 line. Right? Then, or you can also, because Fmax is associated with your delta F, also can be Fmax associated with your sampling rates, 1024 divided by 2.56. Your FFT line is associated with the number of samples that you use to convert to frequency domains through FFT. So it's 1024 samples. Your FFT line is 1024 divided by 2.56. They are dividing at the same factors, 2.56. So this number of sample, we call it a block size, okay, in one blocks. Okay, so delta F also equal to sampling rate over block size. Okay, number of sample that you use to process to frequency domains. Okay, so that also give you the delta F. So the rule of thumb in selecting Fmax, of course, you need to know what is the maximum frequency that you are measuring. So if you have a rotating equipments that probably can go up to, if come with gears, it can go up easily to 50, 60 times of your running frequencies. Then you have to select your Fmax that can cover up to that maximum frequencies. All right. So remember that Fmax and the FFT lines or sampling rate and block size. That decides, okay, how good you want to analyze, how accurate you want to analyze in your frequency domains. Okay, that is your frequency domains in spectrums. All right. So earlier we learned that, okay, if you have a time domain signals, okay, coming in from analog in digitals, so we have all these samples, okay, in times, right? This sample itself, how good is it? Of course, the amplitude itself is defined by your bits, okay, and amplitude resolutions. The x-axis, or your how good is your delta t, is resolution in times, is defined by your sampling frequencies, okay, fs or your sr sampling rates. Right? So if you can analyze in time domains, then no problems. Okay, whatever that you have a very good sampling frequencies, you could have a very good delta t. If you have a very high bits or amplitude resolutions, then you have very good quantizations in terms of y-axis. Then you can analyze your signals, digital signal, very well if you can analyze in time domain. But we are saying that our time domains is very complex in nature. Okay, it's very difficult to analyze in time domain. That's why we go through frequency domain through FFT. All right. So through FFT, your amplitude, your signal in amplitude over time, you will represent in amplitude over frequency in hertz. All right. So to do this FFT discrete is a discrete types of Fourier transforms. Okay, you need to decide, okay, how many samples we want to convert to uh, frequency domain. So here is defined by number of samples, or we say that's block size, because it is processed by number of samples. So here is, let's say, your first blocks. It consists of, let's say, 512 samples. Then continue, and after it complete 512, it will send to FFT. Okay, then it will process your frequency domains. Okay, in frequency domains, peak, give you peak. Then it will collect again 512, go in again. Okay, then another continue. If your signal continue over time, then it will every 512 sample it collects. 512 it collects, then it will go. So this 512 we call it our block size. Give us the numbers of samples. So this number of samples will decides, okay, how good is our frequency domains or our spectrums look like, okay? The resolutions in terms of its frequencies. Because it decides your number of sample that you use in your app, your sampling rates, okay? Then this delta F is your frequency resolution or your bandwidth that can give you to tell you how good, okay, you plot or how accurate you plot this particular frequency domains peak. Okay, so if you have a very good resolutions, okay, for example, you have a resolutions of like this, a little bit wider, right? So probably whatever that you get is a peak like this, but under the same same peak, if you have a smaller amplitudes, so you know better how it change, right? You know how better it change. So or maybe you have in the between you have another peak coming in, right? So probably it will go like this, like this, like this. So you have a better so-called resolution in terms of frequencies. So if you are going to analyze in frequency domain, if you are analyzing in time domain, then you have to ensure that delta t, your amplitudes here, the grids itself is good. Your delta t itself is fine enough. Okay. But if you're analyzing in frequency domain, your complex signal, we said that it's easy to analyze frequency domain. Then we have to ensure that the delta f is fine enough, okay, to 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 give us a good representation of the vibration signal in frequencies. All right. So so to know our frequency resolutions or delta f, right? Right. So basically, it's our sampling rates, SR, divided by our number of sample in the blocks. Is here is block size. All right. Or F max over delta F also equals to F max over our FFT line. So this delta F itself will define how accurate is our frequencies. Okay, when this digital sample being converted or transformed to a frequency domains. All right. So yeah, Nyquist, this one is, you know, that F max is Fs divided by 2.56. F Nyquist is Fs divided by 2.56. F max is Fs divided by 2. You can see these examples. If you want, you will calculate the data acquisition times. You are asked to calculate the data acquisition time and frequency resolution, your bandwidth, BW or frequency resolution, delta F, for a set up or block size 4096, sampling frequency of 204x. So this one is already shown or demonstrated to you just now. I mean, sampling rate 2048. If I'm using 4096, then the acquisition times that I have to wait for the FFT itself is 2 seconds. Okay, 4096 divided by 2048. And the frequency resolution is good up to 0.5 hertz, the inverse of the acquisition times or your sampling frequency divided by the block size. Okay, so it's good up to 0.5. So in the way of you are using F max on FFT line, also the same. Our delta F also equals to F max F max over FFT lines. So that is usually being used. These terms are usually being used in your commercial measurement system or analyzers. But you remember that this F max is associated with this Fs over 2.56. The FFT line is basically also associated with your so-called block size divided by 2.56, or number of samples divided by 2.56, right? Or the N, this is your N divided by 2.56. So it's the same things, okay, just looking at the different aspects, okay, F max. So this F max, this Fs is looking into the full frequencies, but the F max is only looking to the less than the half, below the Nyquist, okay, below the Nyquist, the usables, right? The FFT line also looking into the number of samples available in the usables in frequency domains. So whereas the number of samples that you use to process the entire frequencies of up to your Fs, that is number of blocks or number of sample or block size. All right. So remember the how the fast Fourier transform being processed. Okay, you have to collect a number of samples in blocks, then only it can process. Okay, so that is how it works. Okay, so by doing so, you have to decide, the user have to decide now how many numbers of samples you want it to collect and send to FFT to process to frequency domain. So if that is the case, then it will affect our accuracies or resolution in terms of the frequency. So remember that. Right. So these are some of the signals when you transform to frequencies, how it will look like. Right. So if you have a sine wave, continuous sine wave, it transform to frequencies, then it will give you one sharp peak that we have seen just now, right? One sharp peaks, one sine wave, one sharp peak. If you have a square wave, it will give you a frequencies of 1 over time, the period of this 1 over periods of this square wave frequencies, square wave periods, then plus, okay, the 3 times, 5 times, 7 times, 9 times of so-called odd multiples, odd numbers of multiples of these so-called fundamental frequencies. Right? Transients, right? Transient signal, if you have a sine wave but it's transients, because of the effect of dampings, this is dampened down, the effect of this damping itself, instead of a very sharp peak like what you have seen here, but it go a broad peak. This basically, the horizontal here basically show you the damping effects. Okay, to sigma. If you have an impulse, okay, if I give an impulse in times, okay, then when you go to frequencies, then it will basically give you a straight, horizontal line, as you have seen here, okay, in over frequency. So impulse is a broadband signals, okay. We are saying that it gives you a constant values or constant signals at constant amplitude at a very broad, wide frequency range. Okay. So that is some characteristics of different frequency, different signal when it transforms to a frequency domains. Windowing. So when we want to, that is another so-called possible errors that could lead to the wrong representation or so-called inaccurate representations of our frequency domains data of spectrums. So that is what we call error occurs when we transform to frequency. Okay. Remember, Fourier transforms require the signal to be periodic and infinitely long. Okay, infinitely continuous signals. Fourier transform is infinite signals, infinite lengths. But under discrete Fourier transforms or fast Fourier transform, it is dealing with discrete signals. So you have a finite length, right? So at the finite lengths, because of infinite lengths under Fourier transform analog or continuous signals, so the effects of the beginnings at the and the ends of the signals is very minimum in this case because it's a very long infinite length, right? So under a finite length in the discrete signals, this beginning and the end of the signal becomes an issues. Okay, when will become a significance. The effects will be significance when it go through this so-called fast Fourier transform. Okay, so under fast Fourier transforms, okay, it have to ensure that, okay, oops. Under fast Fourier transform, you still remember we have to set you have a signals, okay, in time domains, samples. We have to select, okay, number of samples, fixed number of samples, right? Which is our block size to process this into frequency domains. Just remember that, right? So this will send to FFT. This will send to FFT. Okay, every blocks will send to FFT to get one spectrum. So it becomes a finite length. Okay, and when it is a finite length, okay, because it's discrete, is a finite length. Okay, so that basically will cause an errors. Okay, especially at the beginning, at the ends of your signals. The Fourier transforms basically it is designed or it is basically used for a continuous signal where your signal is infinitely long. So, okay, when the beginning at the end is become not that significant. Okay, and that is one rules to in the Fourier transform to say that given this length, okay, we have to ensure that the signals, okay, have to start at n at 0 in every blocks. Okay, if no, then the signals will going through this Fourier transform, it will leak out. Okay, then you will cause so-called this leakage, and it will cause errors, okay, in your frequency domains. So what it means here, your signals in one blocks, let's say this is your one blocks, one blocks that will send to FFT. So what it means here, you have to ensure your signals, okay, every block that you send to FFT have to start and end at 0. Okay, start and end at 0. So that if these things is sent to FFT, then no this type of leakage errors. Okay, no issues. But it's very difficult. I mean, because our signal is so-called discrete but continuous, and we are deciding only the fixing on the number of samples of the blocks. So we cannot ensure, okay, our signal for every block can start and end at 0, right? So definitely, if you go through this, then you will have so-called errors. What we call the signal will leak out or leakage will happen, then will cause error in your frequency domains. Okay, it's a computation errors. Okay, for a continuous signal, because it's infinitely long, okay, so you have no this type of issues for continuous signals. Okay, compared to a finite length or what we call a discrete signals, right? So one thing that you can do is you have to take very large numbers of samples, like infinite lengths of samples in one blocks to process. Then probably this leakage will be lesser, or probably not that significant. The errors have no significance, but not that practical. You have to wait for maybe how many let's say 5 minutes, 10 minutes, or 20 minutes just to get one blocks, right? Infinite, very long, times of samples, okay, that you collect and process FFT, right? So no, so it very difficult to be avoided, okay, when if you are transforming your time to frequency through FFTs, okay. Leakage will usually happens, okay. You see that the leakage will, you cannot control the times when it start at n0, then the signal will leak out and you will have this leakage or error coming in. All right. So to overcome this, we use these windowing functions. Right. So FFT computation is done in finite times. Okay, definitely leakage will occur. Okay, effect of leakage can be minimized by using windowing. So what is windowing functions? So windowing function is just another functions. Okay, functions of some sort of these. I mean. Signal functions, some sort of this 0 and 1. Okay, so if you have a signals which is doesn't start, okay, doesn't start at, I draw it doesn't start at 0 and end at 0 right? So multiply with this, right? So 0 at here, right? So it will force this thing, okay, probably to start at 0, because it's any numbers that multiply with 0, it becomes 0, right? So it will force it to start at 0, right? So you probably will have a signal some sort like this, right? So here your start and end, okay, you make sure that it start and end at 0, right? So you won't have the leakage issues in your so-called in the process of transforming from time to frequency domains. Okay, so this going through after windowing functions, going through FFT, then you have no leakage. Then your signals, okay, whatever signal in here, you have a frequency at here, right? Let's say 1 over time, then it will correctly represent this. Right? So that is what we call leakage. So if you see your signal with windowing functions through FFT, then you will see that your signal is correctly represented with one sharp peaks at here, right? If without window, if it doesn't start and end at 0, you cannot ensure it start and end 0, then you have this signal leakage. So instead of one sharp peak at here, you will see some sort of broad peak going like this. Okay, so it's like something like what you have seen just now in the transient signals. It will go something like this, but in fact it is not like this. It is an error during computations. Okay, it was similar like this. So windowing is a process of forcing the end point of the time signal, beginning and end point of time signal to 0, and will minimize. Okay, we didn't say it eliminates, okay, but we said it minimizes the effects of leakage. Okay, so that is how you see here. If you have a continuous not continuous. A continuous so-called digital signals or these digital signals. So this is blocks that we want to process. Every block that we want to process at a fixed number of samples, all right? So we cannot ensure it start and end at 0. So all these block multiplied with these window functions, then we can ensure the signals when it come in 0, when it come out at that block is 0, then the next block come in also 0, when it come out also 0. So we know that every block here now start and end at 0, start and end at 0, then this block will go to FFT, this block then go to FFT, this block go to FFT. Okay, so there are several types of windowing functions. I mean, the commonly used one are Henning and flat tops. Okay, so we will look into this Henning and flat tops. So other types like exponentials also used. If you don't use any window functions or no window functions, then usually it's called rectangular windows. Right, so it's no window functions. So the two main, if you are doing vibrations analysis, so the two main windowing function is Henning and flat tops. All right. So Henning give these two types is the most common. So you will see what is the difference. So this is the functions. This is the functions for Henning. This is the function for flat tops. Okay. So if you see that Henning give more accurate frequencies readings, but reduce the amplitude accuracies by 16%. You can see that. Okay. Flat top give less accurate frequencies, okay, but accurate amplitude accuracies. Okay, so one is good in frequency. If I want to know, okay, how many the exact frequencies components that I have in my complex vibration signal, right, in my spectrums, then probably Henning will be more suitable because it is good or accurate in frequencies. But if I want to know the vibration amplitudes, okay, I already know my frequency is at around 10 hertz. I want to know the vibration amplitude, exact or the accurate vibration amplitudes that develops on my machines, then probably you have to use flat tops, right? Because it gives higher accuracies. So force windows and exponential window usually is for the analysis, the signal that related to force. Okay, we want to ensure that the force only pick up. I mean, the force window is just a rectangular, some sort of rectangular windows. Okay, if you force, okay, whatever signals here to 0, you only capture this particular signal at this particular region. The rest you will multiply with 0. So whatever noises appear at here, multiply with 0, all will become 0. So end up a very clean 0, 1 force, then 0 over time. Right? So exponential windows, if you add, if you suppress it, okay, you suppress this thing to end at 0, then yeah, probably it can ensure that it start and end at 0, the signals, okay, because you multiply the exponential windows that is at the end is 0. So you can ensure the end of the tail of that signal is 0, so you don't have leakage on these particular transient signals. All right. So another questions. All right. In the case of I have a transient signals, okay, going down, very low dampings, okay. After 4 seconds, okay, after 4 seconds, it is still, but you will still see the signal. It doesn't die down to 0, right? So if you multiply with exponential windows, then you can suppress it. Okay, this thing multiply with it, you suppress it. Okay, faster going to 0, right? So this one sent to FFT, no leakage. But how if I don't want to use exponential windows, what can I do? Anyone? What can I do if I don't want to apply exponential window for this transient type of signals? I don't want leakage. Okay, I don't want to apply exponential window. Can I do that? Anyone?
Can we not use Henning?
Cannot. Handing, because handing is the function is some sort like this, right? The start 0. So you will basically force this thing. You see this information, the transient signal, the important information is all at here. You see or not? So if you put a handing window like
Okay.
this, so the end will 0, but the front part also will disappear. So
So
you're
you
missing,
lost the
you'll
important.
miss a lot. Yeah, correct. So what can we do? If I don't want to use window, exponential windows, then I don't want leakage. So what we can do is using a larger block size, right? If you have a larger block size, then your data acquisition time, still remember? Acquisition time for FFT, for collecting the samples is longer, right? So let it, of course, it will go down. Maybe 4 seconds is still not yet 0, right? So maybe after 8 seconds, right, it only come to 0. So 8 seconds only come to 0. So instead of 4096, I mean 4 seconds, I use uh 1024 and 4096, right? Just now, sampling rate and block size. So at 4 seconds, it doesn't end at 0, right? So, but then if I go up to 8 seconds, 8 seconds at here. So if I increase this to 8192, so my acquisition time is 8 seconds. So I can actually wait until 8 seconds. When it dies down to 0, then only I take it. Okay, then this thing will send to FFT. So of course, you will compromise on the time, but then in this case, also can achieve the signal that without leakage, right? It can ensure that it end at 0 by itself, not by forcing. Because when you do this forcing, I mean, you have to compensate it back, because it will affect, because this type of signals, a decaying signal, it come with some sort of dampings, okay, by itself, right? This 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 itself is damping, and now you are forcing it, you are adding more damping to this type of signal. So later on, when this thing, even without leakage, after you force it without leakage, the transient signal the frequency domain, the spectrum itself is broader. So even without leakage, and you are forcing it, it will go, because the damping is larger, it will go broader. Okay, so you have to compensate the weight, the what we call the damping of our exponential window functions, additional added to the existing transient signals. So have to compensate it back. So if possible, if you don't want to use it, then you have to wait until it's end at 0. So if your system is high dampings, okay, the signal is high damping, very fast. If it's high damping, meaning it decay very fast to 0, maybe in 2 seconds is done, then probably you do not need exponential window at all, right? So you can straight away use 1024 2048 in within 2 seconds. You get a very good signal when it starts at n at 0. All right. So remember that you can still play around with the number of sample that you use in the blocks to process FFTs. So if everything good, then your time domain is the what we call the most informative so-called signals that can be used to analyze. So just that, I mean, in time domain is a little bit complex, okay, but it doesn't mean that it's not useful. So we also have several analysis that can be only performed in time domains, where frequency domain a lot of time are not so easy to perform. Okay, so there are various treatments that can perform on the time series, including the integrations, right? So you remember we say that the because of the advancements of digital signal processing, okay, we do not need the analog the signal conditioners, where you have these integrators or differentiators, analogs at signal conditioner sites, the hardware sites. So you can now perform, okay, in digital sites, okay, the digital signals, okay, where you can perform this only in time domains. When the signal is still in time domain, time series, you perform integrations, differentiations easily, I mean, through these digital signals, right? So with this, then you can see that the signal conditionals, if you want integrators, differentiator, actually, in this case, you can do it at what we call digitals. Okay, once you have convert everything into digital, then only you start perform all these things, right? So that allow us to use accelerations or astrometers now. Okay, and IEPE types. You see that, I mean, that is how convenience now. Using IEPE type, you have these built-in amplifiers. Okay, where you amplify the vibration signals. I mean, the signals in voltage. So that you can be read by these DAQs, right? So DAQ, because DAQ provide a constant current 2 milliamp to that's the amplifier itself, preamplifier itself. So you have a very good signal coming in without directly connects to your DAQ without that signal conditional. External signal conditional sit in between, right? Then coming in, okay, you are measuring accelerations, everything in the, of course, in millivolts, and you have this sensitivity, then it basically converts to the accelerations. So under this time domains analysis, then you can do integration from acceleration to velocities. Then we have the velocity signals, then we can get velocity amplitudes, by velocity overall vibrations. Then a lot of times your ISO standard compare with these velocities, RMS, overall RMS. Then yeah, you can immediately using this in digital domain compare with whatever that you are referring to the standards, right? So it can be easily done in digital domains. So you can do integrations, you can do differentiations, no problems. Similar, another one is the bandpass filters. So like your, of course, if like your anti-aliasing filters, that is an analog low pass, and we mentioned that is a low pass analog filters, right? So that part is already built in into the hardware, okay, on your DAQs. Okay, that is to take care all these wrong representations of our time signals. So, but coming in, I mean, those signal coming in discretized into digitals. So it could be also very complex, very noisy. So, okay, you have a lot of, I mean, from the environmental, so I mean, the noise from the environmental. So sometimes there is the needs, okay, to filter out, okay, those unwanted noises or unwanted frequency that we are not interested, but it actually contaminates we know that it contaminates our overall signals. So it can be also done in digital domain now, in time domain and time domains of our digital signals. Okay, then we performing this bandpass filters to filter out, okay, the signal that we do not want. So, okay, in terms of its frequencies, we do not want those frequencies. Then components, then we only focus on a bands of a frequency that we want to analyze. We can also do these statistical operations also, because it's time domains. Okay, everything is raw. So the overall RMS values, the basically it can immediately tell us where is the maximum values, where is the minimum value. That is consider, because you see, I mean, these time domains, the vibration signal, it consists of all types of frequency components, okay, available in that signals, okay. So it could be, let's say, for example, you have a 5 frequency component. It could be, uh, let's say you have a 10, 20, 50, 10, 20, 50, 100, and 150. So it could be 100 hertz is a very high vibration amplitude. But in this case, in time domain, basically it convolutes or superimpose everything together, right? So we, if you apply this statistical operation, we can know, okay, overall in this particular vibration signal consists of 5 frequency components. What is its maximum values? What is its average values? What is its RMS values or standard deviation or variance? So, and it can be easily obtained, extracted out this particular information in time domains. If you are in frequency domain, of course, it still can be done, but then if you have 5 frequency components, then you have to take each frequency components and you have to compare, or if you are taking RMS, then you have to add them up. So basically, it's another additional works for you. So in this case, in time series or time domains, these statistical operations can give us an ideas, okay, an overall vibrations in terms of its RMS, maximum variance or standard deviation. Basically, it can give us an overall so-called idea, I mean, on that particular signal strengths, okay, that we are, or vibrations severity that we are actually capturing. So. And time domains, okay, because how to say it, your time domain basically is a dynamic signals. So dynamic signal basically, if you have 2 time domains or two dynamic signals, so you know, right? So the directions of, if you can compare, you know the directions of that 2 signals. So when this signal going up, uh, so like what I mentioned earlier, so you know the direction. If you have a 2 time domain, then we know, okay, let's say at the same frequencies, then you know that when this one going up, right, this one will coming down. So you know that they are in opposite direction. And because you see this virus time domain itself, it have its amplitude and it have its also directions. When it compared to another signals, you have its directions, okay, relative motion or relative directions. So because of this, it can be easily adds. Okay, you can perform this arithmetics easily under this so-called time domains. So you can add up 2 time domain signals easily just by these additions, or you can even subtract them. Okay, 2 signals over times. Okay, that is over times. So at the same, from 0 seconds to 1 second to 2 seconds, the changes, okay, you can do subtractions, you can do additions on these 2 signals easily, right? So where in frequency domain is not so possible. And you can use it as a logical true or false. Okay, you can use it to set, for example, an alarms when it is high. Then what should I do? So, okay, you can do so-called these logical things in also time domains. Or when you're at 90 degrees, what is your amplitude going above what frequency or so above what amplitudes, then you can do some perform, okay, some actions, okay, so that can be done through this logical also. And that is some of the time domain analysis that can be performed, I mean, in your signal when your signal is a time series. Whereas frequency domain, as I mentioned to you, the spectrum itself is the very useful so-called information that we can use to analyze vibrations or what we call machinery faults. I mean, use this vibration as a parameter to diagnose okay, machinery faults. So of course, you have this forward FFT, like what I mentioned to you. Okay, so from time domains, okay, converts to using this forward FFT, you get the frequency domain or spectrums. So this spectrum consists of it basically separates, okay, all these frequency components available in this time domain in frequency. So like what I showed you earlier last week, then you have 10 hertz, 20 hertz, 30 hertz. So you know each frequency components, which frequency is more dominant, higher in terms of amplitude, and at what amplitudes, what extents, right? So that can be done easily in a frequency domain. Of course, right, in frequency domains, I mean, you can easily with this inverse FFT, IFFT, it can also back transform to a time domains. So if you have a frequency domain with this IFFT, then you can also convert back to a frequency domain. So also it's parts of the what we call the analysis where you can do this frequency domain. So sometimes it is needed to analyze, okay, and do some processing or like filtering everything into frequency. When you in frequency domain only you can see, okay, what are the frequency components that you do not want, right? So from there you can filter them, okay. You can what we call remove them, okay, in frequency. Then back transform a cleaner so-called what we call a time domains, time series signals, right? So that's through inverse FFT. And waterfall spectrum is another one's our spectrums, just that the way it is being plotted or cascaded. So you have a what we call spectrums plotted over a series of times. So in 1 second, 2 seconds, 3 seconds. So maybe every 2 seconds, it plots a spectrum. So from there you can see, okay, the change of your vibration amplitudes in terms of different frequencies over times, right? So you have this waterfall spectrums, okay, it's also similar to cascades spectrums. So cascade spectrum is plot over speeds, change of speed. So if a speed change, then you will plot a FFT. Another speed change, you will plot a FFT. Usually used for what we call when the machine is start up from 0 to its running speed, running frequencies. So you will, when it start up from 0 to let's say 100 hertz, then maybe every 1 hertz you plot its spectrums, its FFT, sorry, or its spectrums. Color intensity waterfall spectrum is another representations, okay, of this waterfall. Okay, basically is instead of looking into its spectrums, so it is represented by these color contours. So this color contour give you the intensity of the vibration amplitudes. Right, and transfer functions is another ones that can be plotted in or can be analyzed in frequency domains. So transfer functions, if you remember what you have learned, like in vibration, in controls, you have this TF equals to out over ins. So usually this out over ins is output over input. Right. So this outward in, you have output signals, like you have let's say you have an output signals, right? Then you have probably an input signals, right? So usually you don't, when you want to find transfer function, you don't use the times divide by the inputs. So what you do is you transform to FFT. So you have these so-called frequency domains, right? Then divide by your also your frequency domain of these inputs, okay? So probably like this, right? Then you get what we call these transfer functions, right? So this is what we call the transfer function out over ins. So that only can be done in frequency domains. Coherence function is another measurements. These two are later on, I mean, in our very advanced topic later on in the last few weeks, we will look into how to perform that test that where we cover these two so-called functions to to perform this test to evaluate uh, that quality. I mean, you still remember the quality of the things. Performing this DDV, that is part of a procedures where we want to evaluate whether this machinery are undergoing or having these dynamics, structural dynamics issues or not. So this transfer function and coherent function basically is in frequency domains and only can be analyzed in frequency domains. So this transfer function basically give us the out over ins, and whereas this coherent function is to measure the noise appear in the outputs and the inputs. So compare with its earliest results. So basically, it's a tools or it's a functions that can use to measure how repeatable is our results, whether the outputs and how repeatable is or how reliable is our so-called this transfer functions itself. So this coherent function is to measure whether your results of output and inputs is repeatable. Okay, it comes with any noise in either its output and the inputs. So that can be reflected in these coherent functions. We will discuss these two in our later topic. But for at this stage, okay, you know that these two functions only can be done in a frequency domain and is parts of a frequency domain analysis. All right. Next is what we call overlappings and averagings. So what are these? So if you remember, this is additional things that you probably will find it useful in order to get a better result. So this is to help us to improve. Okay, either I mean the overlapping is help us to improve to optimize. Okay, the times taken to use the times used to take the data. Averaging is to ensure our data is sufficient, is accurate, and it repeatable itself. So these two features, and you will see quite common in your analyzers or commercial analyzers that when it comes with this software itself, it will ask you to define whether you want to do these overlappings and how many average you want to take. And this average is related to the numbers of samples in one block that we decide earlier. So if you remember, we said that our signals, if we want to convert to frequency, we need to decide the number of samples in one block to process these FFTs, right? So you have to wait. Okay? The acquisition time is based on your sampling rate and block size. So you have to wait, right? So uh, we don't just take one set of blocks, one blocks, then we perform FFT, then end of story. No, right? So usually you have to make sure your data is good enough. I mean, any experiments that you have done earlier, you have learned earlier, also you need to do some few times, right? You have to repeat this test for a few times to get this average to make sure your result is reliable, so it's good, it's repeatable, right? So similar like this, you also have you don't just take one blocks, right? You just take one block and you stop, and then the FFT itself is your final results. No, so we usually will take several blocks, and you take these several blocks, then you average it, and you get the average so-called spectrums or FFTs, right? So if you for example, if you are using 2048, let's take one example. Block size is 4096 samples, right? Then your fs or your sampling rate is equals to 2048 samples seconds. So what we have learned, all right, your T or your data acquisition times will be uh your PS over SR. So it's a 4096 over 2048 equals to 2 seconds, right? Then your delta T equals to SR over PS. So it's point 0.5 2048 over 4096 equals to 0.5 hertz, right? So that basically give you this information. So if you see that, if you are taking, you don't just take one blocks 2 seconds, then end of story. No. So usually we take, for example, take 10 blocks, right? So 10 blocks, you need 10 times to 20 seconds, right? So you need 20 seconds, you have to wait 20 seconds to complete that particular measurements. In this case, then you have your every 2 seconds, you have one, it will basically process and give you one FFT or spectrums. Then every 2 seconds you have one. So total you have, if you have 10 blocks, then you have 10 so-called FFTs. So averaging is to average all these FFT and give you this 10 FFT and give you a one so-called average FFTs or spectrums. Overlapping is a processor. I mean, use basically sharing. Okay, they are sharing some sort of data. Okay, from previous your upcoming so-called blocks of samples. Basically, you are sharing some portions of your previous blocks so-called samples because these signals because this signal is continuous. The signal is not, I mean, what I mean, not the continuous analog signals. What I mean here is a digital signal, but it is, if you continue, if you take the digital signal, is continue, right? So, but in this case, you select, let's say, 4096. So let's say 4096 is these blocks, right? So another one is finished, you will go FFT, then you will take another blocks, go FFT, another blocks, FFT, right? So instead of doing this, you have to wait after it finish every blocks, only it takes. So then you can also decide, okay, yeah, because I want to save some times, right? You can perform, okay, this was one block, but I want to share probably half of our previous block with my the next blocks. So then you finish it, then I will share another so-called the third blocks. I will share another so-called, when I finish this, so I will share another half, right? Share another half with the previous block. So in this case, you will save the times, right, of acquisitions. You are still getting three FFT, but at a shorter period of times. Right, so overlapping process use some percentage of previous data blocks to calculate FFTs. So it allows shorter data processing time. So that basically to helps, okay, is helping to reduce this. Okay, if you no overlappings, so getting 10 blocks, 10 blocks of FFTs, so you need 10 times 2, so it's 20 seconds. So if you are using overlappings, so you are sharing some portions of your previous block data for your upcoming blocks, then you will definitely less than these 20 seconds. Okay, so typical overlapping settings are 0%, of course, no overlap 25, 50, 75, 90, and maximums. So this maximum is referring to uh, the times, okay, taken. Once is finished your FFT, then it will immediately take. So I need to highlight a little bit on how it works. So these overlappings, you have to use it with precautions. All right. So if you see, I mean, if you get block once, right here, if you get the first blocks finished, then you will perform FFTs, right? But because currently the FFT what we call is quite very fast, right? When to compute this FFT is quite very significant and very fast already. So it will be less than probably 1 second. Maybe in millisecond, you can already compute one blocks of FFT already. So in this case, overlapping have no issues. But last time, I mean, when it's not so fast, so probably you have these one blocks, right? Right? You have this one block, first block. Then you perform FFT. It takes this. After you finish the one block, only you can perform FFT, right? So that give you another blocks, right? So how to say it? If you don't do overlappings, then after this you have your second block, so right? You have your second block, block 2. Then you finish from here. Okay, you have another FFT, right? But last time when these Fourier transforms or this DFT is very slow, then there is a need of doing overlappings. You see or not? I mean, if no, then you have to do block finish. You have to wait 2 seconds. You have to wait for another the time that it convert to frequencies, the computation of FFTs. Then only you can start with the second blocks. Then only you do FFT. So that was last time. And in this case, overlapping is you will see that it is more significant and it's actually really needs these overlappings. But because currently, I mean, your FFT is being computed so fast. So in fact, you can see that your FFT probably when you have first blocks, right? So that is your block 1. So right after block 1, probably you need this for FFT, right? Then you could have your block 2. Then you have another FFT, block 3. Right? So it's very small times difference. Okay. So the whole ideas of this overlapping is to making use of these times, right? So if you can, when it's doing this FFTs, why not I take the previous data? Okay, my block 2s, when it's doing these FFTs, why not I take I start taking block 2 data. Basically, I'm taking here until here, right? You know, so that is the whole ideas of what we call overlappings. But there is also some cautions you have to also take notes when you do FFTs. So so as long as your FFT is fast enough, right? So actually, overlapping probably is for me is not so needed because it's basically it can happen very fast and you don't even see the difference. You still wait 2 seconds every 2 seconds to complete one block and immediately real time you will see FFTs, right? So that is not really a need of doing this overlapping unless, right, you want to really save some time, you want to use some shared data. So yeah, you can actually use it. But then you remember that the length of the data that you are taking, the raw data here, I'm talking about the time signal, time series of data, the length, if you are doing overlapping, the time signals is shortest lah. The actual time signal that you are capturing will be shortest if you are doing overlappings. So if you are not doing overlappings, then every blocks you will have this size, right? So you have another size, then you have another size. So you have a longer size of time signals. Of course, it will save. If you do overlapping, you will save times. You will save your space, but the the what we call the bad things is you lost more informations lah. In this case, you have lesser so-called time series signals. Right? So you might lose information. Okay. So we have to ensure, okay, this so-called.
Just one question. How about the accuracy, whether it will become less accurate if you do overlapping?
Yeah, I mean, depends. I mean, you're talking about the accuracies, right? So coming back to what will affect your accuracies. So if you are talking about the what we call sensor itself, right? If we're talking about this overlapping itself, as long as your signal is stable, right? Then actually overlapping won't affect your accuracy. We are more concerned on the actual vibration signals. It's not pure sine wave. You see or not? You have a lot of signal coming in, and sometimes it is not really steady. You see or not? When it's not really steady, I mean when you are doing overlappings, then it will affect accuracy. So that comes the second statement here. Only applicable to a steady state periodic signals. All right, because they are sharing signals. Okay, because they are sharing signals. So if you are assuming this signal is steady over times, okay, then sharing have no issue. You see or not? I mean, because one block itself, this block itself of signals, you use it or you share with this. If you look at these time signals, let me erase it. So because they are steady, right? So if you see that if you are sharing, you have actually no issues. Okay, if you are sharing, you have no issue because they are same, right? These particular parts, if I don't share, then I'm taking longer time, but I'm taking just this particular part. So you see that the front parts of this and the front and this particular sharing, if I share, so they are same, right? So for steady states, you can use it. You can use it, and it helps to save times, right? Particularly during old time when you FFT, you take you a longer times, right? But in this current technology that you have, FFT can be performed very fast, right? So of course, you can still apply this overlapping because I don't want to take so long times because I know that the signal is steady, right? Provided you know the signal is steady and you want to save more times, right? Then actually you can perform this overlappings, right? It won't affect accuracy because you already know this signal. When you want to use overlapping, you must know your signal is steady, right? You have to know. When you know it's steady, meaning you have a very steady amplitude, right? In this case, overlapping, no issue. It will save you times, and yeah, accuracy not affected. Okay, basically you are still performing the FFT, provided your sensors, the hardware, the software, how you perform the FFT is correct lah. I'm talking about overlapping itself. Okay, it won't actually affect. And the rules is it have to be a steady state periodic signal. So you are very confident that okay, this signal is very steady states. Okay, it's a steady signal. Then yeah, you can use it. But a lot of times in the actual situations, it is very complex, right? It's not a very steady. It could be not steady, okay, because it come with randoms. A lot of noise coming in. This external noise that we are sometimes we are not sure, okay, they are really noise and definitely not steady, and the intensity of this noise we also not sure, right? So in this case, if you are applying this overlapping, you might have issues. Okay, you might have issue when you are dealing with these unsteady signals, right? In terms of you will later on the next slide I will show you when it is not steady, so what will happen. But that to answer you, if you very confident your signal is steady, then no issues. All right. If no, then if not no, then I will say don't do overlapping. So myself, when I do this analysis or data acquisition or data processing, then myself I don't do overlappings. So of course you can use it. Okay. So if you are talking about max, max is basically is to share the maximums. Maybe it's not the 100%. Maximum is to share up to the times. Okay, that cover the time up to your FFT being computed. So you still need times to compute your FFTs. So if like for example here, so I will, let's say this is the time that I use to calculate FFT. So the maximum is the maximum so-called overlapping is that block, so right, this block. The second block is the green one. So you are only using, okay, a very small amount of so-called the block ones is full, these full blocks. The second block itself, you are sharing quite big portions of your first block signals. Only this particular parts is a new signals. Okay, only this particular part is new signal. That is maximum, right? So you're sharing a lot of these are basically is based on the speeds of your FFT. So FFT faster and you sharing more. Okay? So in this case, your FFT take longer, right? So the maximum is like this, no? So you are just sharing these particular portions. Okay, so these particular portions itself is a new signals. Right, so that is maximums in this case. So why I said overlappings process is not recommended when your signal is not steady or is transient or random events. So take these examples when your overlappings is not suitable. All right. So when you have two frequencies, I mean two sinusoidal functions, when it come very close to each other, you have one this phenomenon called beatings. Okay, so later on we also look into this. Is one of the analysis of faults that we can have a look. It's not really fault, but then it is causing your high vibrations. Okay, so if you look into this, when you have a beating happen, a beating phenomenon happens is when you have a two close frequency come to each other. So this, if you want to relate this to actual condition, then you have probably two identical machines sit side by side, right? And one is running at 100 hertz, another one is running at let's say 99 hertz, okay? Or one motor is running at 50 hertz, another one is running at 48 hertz. So they are very close. So when they are very close, they tend to, of course, this vibration will transfer from one to one, unit to one unit. So when you pick up, you will pick up these two very close frequencies. Okay, so in this case, you will have so-called at one time, this particular, it is like a two sinusoidal addition of two sinusoidals. Okay, it is like a addition of two sinusoidals. Okay, when these two sinusoidal with a very close frequency add together, it will give you some sort of vibration signals like this. Okay, At one point, they will cancel out each others. Okay, where you have a very low vibrations. At one point, this will go up. The vibration will go up very high when they add up together. At one point, when they are in phase, they are add up together. So you will see a what we call steady signals when you can go up, down, like this. All right. So if you are doing overlappings, right, then it will become so-called an issues. You are sharing every blocks. You are sharing. You see, let's say I'm taking this at my first blocks, right? Right. You see, my first block, I have a signals of going up, then down, and going up, right? And second block is because I'm sharing, right? I'm sharing or overlappings. So for example, like this. So my second block, you see that is going down, is going up, then coming down, right? So you see that the block ones and the block two signals are different. So your FFT will be different, okay, in this case. So that is the reason when you do overlappings and your signal is not steady. In this case, it's going up, high, low, like this. Due to this beating phenomenon, or what we call a very close to frequency coming in, then you will have an issues because the FFT of the first blocks and the FFT of the second blocks probably will give you different information in this case. Right, earlier we said that because they are steady, right, the FFT of these blocks, right, compared to FFT of these particular block, second blocks are same. Okay. So it's repeatable, right? So if they are same, then it's repeatable, so your result is good. But in this case, your result is not repeatable, or every block of spectrums, then you will become an issue. So overlapping only advisable, okay? When you want to use it, only use it. It's advisable to use it when your signal is steady, or your vibration is a steady state. Right. So that is one thing. The other things, even you say I can get more blocks, okay. Then I do an averaging on it, then I probably will get a good result. Also, no, not really happens in this particular case when you have a beating phenomenon. So if you see that is the first block, you have the blue block signals. Maybe I put. So you have this block. So this FFT will give you one probably a signal like this probably. Then you have second blocks coming in because you are sharing, right? So you have this FFT. Then probably it will give you a little bit probably different signals. So when these two coming in together and do an average, so you won't get a consistent results. So we can do is we have to ensure, okay, the blocks that we obtain covers the entire or larger than the entire beating periods. So average must consider sufficient sampling time in order to capture the entire beat periods. So if you have this particular case itself, then you see that there is a change. There is a change of what we call. There is a change of this amplitude going up, down, up, down, up, down. So this is what we call the beat periods, right? So if you can cover the at least the sufficient times, I mean, your block itself, you can cover the entire beat periods. So probably like this itself, right? So another block is like this, right? So then you have a what we call sufficient information of full frequencies, full this particular part itself. So you won't miss any informations in this case. All right, so I have to take notes on that. So if this FFT, then if you're doing averaging, also matters. But overlapping definitely not advisable in this case. If you are doing overlapping, you do not know really when it starts and when it stops. I mean the change. Okay, the change is difficult. Only know, yeah, it will be the bit periods. You will see in time domains. Yeah, it will be uh, every frequency, the difference is tens. So 1 over 10 is the time is 0.1 second. Every 0.1 second, you have this change of amplitudes. So that basically give us some ideas on when, how long I need to capture for one blocks. Okay. So that is one block, but it doesn't give us information on how much so-called percentage I can share, the overlappings. Okay. So it happens when you have a two close frequency come to each other, and it's very frequently see this when you have a two machine coming into play side by side, running together. Uh, then they are very, of course, you said it's running at 50 hertz. Definitely, it won't. In actual, you have, because of the sleep itself, you have slightly lower than that 50 hertz. So maybe it's 49. Another one is 48. Different sleep frequency coming in. Uh, then it becomes two close frequencies. So if it's two same frequency, exactly the same, then no issue. But because you have certain some difference, so that basically will cause this so-called fluctuates of your vibration amplitudes over time. Lesser, okay. If you have a less difference, then your fluctuation will take longer. So if you have a 1 hertz of difference, 1 hertz difference, let's say 49 and 50 hertz. So the bit frequencies will be 1 hertz, right? The difference. Then the bit periods is also 1. 1 over 1 is 1 second. So every 1 second, let's say this is 1 second, this is 2 seconds, this is 3 seconds. So you will see the vibrations. I mean, it probably will go uh, uh, to sets. Probably will see vibration go up, down, then up, down, then up again, slowly up again, okay, then down again, then up again, down again. So it will basically, you will see a periods of like this, which is at 1 second. Right, so some sort like this will happen, and if that is the case, then overlapping is not suitable, or a signals or transient signals like what you have learned earlier, like this, so you don't do overlapping also, right? Next is averaging. So right, so if you know when to use overlapping or not using overlappings, okay, you know that they are processing, and also you know that this FFT is processing in blocks, right? So these blocks of FFTs, I mean, it can be average, okay? So the purpose of averaging is to ascertain repeatable results or or reduce noise, right? So averaging can be done in time domain or frequency domains, okay? So if you have convert everything into frequency, then you average, that is called frequency domains. So before you convert, you do averaging, that is time domain. So you have your time series, right? Sorry, I draw it. So you have your time series, then undergoing FFT, okay, then you have frequency domains, right? Hertz times, right? So that is one blocks, 2 second, right? So you have another blocks continuously, you have another blocks, All right, 2 seconds. So you have another signal similar because steadies, right? Another 2 seconds. Then if you these blocks, if we use this block plus these blocks of signal, then divide by 2, right? Then that is what we call the time domains. If you are using the process FFT plus another process FFT, then divide by 2, that is our frequency domain. So this averaging is a so-called blocks averagings. Okay, it's every blocks of this signal you take it and average. Okay, it's not averaging on your signals of blocks. It's not like averaging on the entire this block itself. I average this signal amplitudes. Okay, it's not like this. So end up your signal basically will become 0 if you average. If you have these signals, right? So is once you capture blocks, okay, then either you process the FFT, then take it. Then the second block coming in, FFT, take it, then you divide. Okay, the first one coming in, divide by 1. The second one coming in already, then you plus, divide by 2. Third one coming in, plus 3, divide by 3. Right? So that is blocks base of analysis averagings lah. Right? So time domain averaging is useful in reducing noise, particularly. So if you have a lot of, very noisy signal, performing these time averagings, it will help to reduce noise. But frequency domains is more towards reduce non-linearity, or what we call mix your results more repeatables. So because whatever that you get here, you assume they are similar, right? So the whole idea is to smoothen, okay, this particular so-called FFT in this case, right? It is to smoothen your FFT. So it's more towards smoothen to get repeatable results. So 4 types of averagings are common. You have a linear averagings, exponential averagings, peak hole averaging, and time synchronous averaging. So 3 of these 3 is all referring to frequencies, domains averagings. So this itself is, as the name implies, time domains. All right. Then let's have a look on this. So linear averaging is a frequency domain averagings. Okay, FFT is added n times and divided by n. So it's like what I mentioned to you, right? So you have a first coming in, divide by 1. The second one blocks coming in already, FFT, you got the FFT already, then you add the first one, divide by 2. Then the third one coming in, divide by 3, something like this. Okay, so it's to obtain repeatable, more repeatable results, the whole ideas. Okay, and it's the most common forms of averaging. So exponential averaging, that is it's also a frequency domain averaging. The most reason FFT is considered more important than the first measurements. So a lot of time when you start the measurement, probably you it's still not stable. The machine is still not stable. Maybe you have a lot of noise coming in, electrical noise or whatever is coming in. So probably if you are using exponential averaging, so it is some sort of given multiply your average with a weightage. So the latest one will give the weightage of 1. Okay. Then the reason one, the new one, the old one, will basically you have a smaller weightage in this case. So you give a higher weightage. Basically, you multiply with that higher weightage of 0.9 on your O1. The new the 0.1 is a O1. New one you have 0.9, something like that. So that is the whole idea of when you do this, okay, with the weightage, then you get the reason one is more important, then you get that result, which you know that it is more repeated, more so-called accurate. It's the reason ones. I mean the old one probably you when it's just started, it's still not so steady yet, but you start taking it already, so the weightage will be smaller. You put a smaller weightage lah. So it used to examine conditions that change slowly with respect to the sampling times. All right, so probably you have some changes of conditions. So then haven't go to steady yet, then yeah, that exponential averagings. Okay, the whole idea is you put a weightage, okay, on the reasons. Okay, but else this linear averaging is the most common and most useful one. Peak hole is also a frequency domain averaging. So the peak value at each frequency are recorded and displayed during the averaging process. So it's used to observing transient events such as run up, close down, or random events. So the whole idea of this is to records. Okay, you have the first blocks. Okay, coming in, right? So you have let's say you have first block at this peak. This frequency is this peak is a 5 mm per second. So of course, if you take this divide by 1, right? Then if you are using peak hole, so the second one coming in is 4.8, right? So it will still show you this, right? So that is the peak maximum that you have, right? The third blocks coming in, this is block 1, the 2, 3. You have a slightly for 5.1, okay, mm per second. So the if you're doing this peak hole averaging, then it will show this, right? You will show this. Then if you another blocks coming in is 5.12, then it will show this. Right? So that is a peak hole. So if you have a transients run up event, then you know, okay, how the it will only keep the what we call the maximum levels frequency components, the amplitude components. Then you know, okay, when during these changes of events, I mean this during this so-called change of conditions events or random events. So what the maximum ever vibration amplitude that it can achieve or obtains, okay, or recorded during this change of condition events. So that basically give you some of the information, right? So that you have to use a big hole. Time synchronous averaging is time domain averaging. So it is done by synchronizing the desired frequency. Okay, so usually you have a reference frequency. Okay, so it will only refer to that reference frequencies. Then whatever frequency that appears not be reference to these reference frequencies, all through these time domains will be removed. So especially those noises coming in when it is not synchronous with all these frequencies, the reference frequencies, for example, the tachometers frequencies, then it will be over this time domain averaging or time synchronous averaging, it will be removed. And it will only keep those that synchronous with these tachometer frequencies. Okay, that is time synchronous frequency. So vibration signals that are synchronous to the frequency will be averaged, while others will not be considered and will be over time it will be removed. So that is what we call it is suitable if this averaging technique is suitable in reducing noise. So those non-synchronous we consider them they are noises, right? So you can be remove it. So it improves the signal to noise ratios. So your signal strength becomes better, higher, then you will those noise will be reduced. All right. So finally, if you have this overlapping and averagings, I mean together, so it's like what I have mentioned to you. So if you are sharing half the R or it, so instead of taking 3 blocks, let's say this is 1 second. Let's say this is 1 second. So if you want to take one block here, you need 2 seconds, right? So if you want to take 3 blocks, then you need 6 seconds. So 3 blocks, you need, in this case, you need 6 times 2 seconds. You need 6 seconds. But if you are doing overlapping, so you are sharing half 50%, then in this case you can see that you only need how many seconds? 2, 3, 4. So if you are sharing half, you only need 4. So this is for the measurements so-called equation that you can use to calculate a total measurement duration in the case of you want to perform overlapping of your signals inbox. Right. So averaging is like I mentioned to you, this block sent to FFT, you get one spectrum. Then the first, of course, divide this signal divide by 1, right? So the second block, when it got it already, then you go to FFT. Then now you have 2 spectrums. So this 1 plus 2, then you divide by 2. Then if you have the third block already, then you have the third spectrum. So you have 1 plus 1, 1 plus 2 plus 3, divide by 3. Then you have a final so-called average spectrums. All right. So that is about overlapping and averaging. So there is needs for averaging, but overlapping is up to your own choice. Okay, whether you want to use it or to share it or not. In the case of you are very confident that your signal is steady state, then yes, why not? You can do it and you can save sometimes.